exactly by this linear part of the curve, okay? So, what we tend to find is at some point that behavior breaks down. There's a turnover here, and usually at this point, we'll take a look at what's happening. It seems to be that once I reach a certain force, stress applied, then this thing sort of changes length and doesn't really need any increasing applied force. So this is going to turn out to be, in fact, a region of permanent deformation. And then eventually this thing actually breaks. So this thing doesn't make any sense anymore, so this thing actually breaks at some point here, okay? So this is a sort of general type of response. For us, we're only going to work in that first linear part where we can characterize things nicely. But take this as an example. Rubber band, relaxed length, more or less. I take this, I pull on the ends. This is a tensile stress. I'm going to have a tensile strain. So at this point, I'm stretching it, I'm stretching it, I'm stretching it, and as you know, a rubber band, if it's doing its job well, will go back to its original length once I release the strain. This is not a good representation in terms of when I'm compressing it, because it becomes, it's no longer taut. But for this stretching behavior, it's a pretty good example of the linear domain of the stress-strain relationship. It's hard to find a material that's good at representing both the elastic region for small stretches, small applied forces, and the permanent deformation region. Not many materials will illustrate those both nicely. Here's a piece of putty. You will almost never see this, but I can slightly exert small stretches and small compressions, and it will in fact go back to its original shape for very small stretches. But in general, as you know, for a piece like this, if I stretch it like so, and I let the thing go, well, it certainly isn't going to go back. So it's reached the region of permanent deformation, okay? You can go ahead. Now here's my permanent deformation region, and of course, if I keep going, I keep going, I keep going. So, simple model. For those of you particularly who are engineers, you're going to care about these things a lot. There are tables in our textbook that characterize the different types of responses of materials to these types of stresses, and that's the last thing we're going to talk about. And somewhat miraculously, we may even finish early today, but I do want to do a worked example on this before we wrap up. So, all right, let's characterize this region. Linear response. So, for, let me call it small stresses, which means before I get permanent deformation, it is clear that strain is proportional to stress. That's the linearity a la Hooke's law that we're going to profit from, okay? So if that's true, I can, with any proportionality, replace my proportionality with a constant, and we're going to get equations that reflect the linear dependence of the strain on the stress. And again, for engineering purposes, the coefficients of proportionality are designated differently, and again, for those of you who are going to be mechanical engineers, this is going to be a big deal. So, tensile, shear, and hydraulic. I'm going to have to refer to my notes here because I can never remember these things. Let's see how this goes. So I'm going to write this up. So the constants of proportionality are usually inverted compared to what I would describe as cause and effect. Not a physicist's way of doing it in general, but here we go. Okay, so I think this is following our textbook notation. This is for the case of tensile stress. So I'm applying a stretching or compressing force along the length parameter of interest. So force per unit area is the stress, is proportional, and this is called, you may get this right, Young's modulus. Okay? I'm more used to actually seeing this represented with a Y. But again, I think I'm following our textbook with an E in this case. If I'm not, just replace it by whatever your preferred symbol is for the concept of proportionality. So whenever you hear about Young's modulus, it's representing something about the response of your material to a tensile stress, okay? And again, for those of you who are interested, look up the varying ranges of this Young's modulus in our textbook for certain common materials.
Our book also uses Y.
Okay, thank you. I don't know where E came from. All right, so Y is more common. Good. All right, so that's the tensile. What about for the shear stress? So, in this case, constant of proportionality. And it sounds like you have your book with you.
No, not with me. I just remember.
You remember?
I remember all of this Y.
So, again, I'm not exactly sure if this is the common symbol or not. G. This is the shear modulus. And lastly, kind of almost out of space, but not quite, force per unit area. In this case, remember this is a hydraulic stress that's being exerted. You can think of it as pressure, or at least an overpressure, perhaps, if you're working with reference to a baseline pressure. I'm just going to put this in parentheses that it's a pressure. And then this one is the one that I actually do remember, because it's, to be honest, one that's a bit more used by physicists. And it is the so-called bulk modulus. Okay? So let me just have you look at these for a moment. And again, these coefficients are simply measures of how elastic or compressible or deformable these materials are. And so very often when you are working engineering problems, of course, you need to know these things so that you know that your materials will appropriately respond to the types of forces and pressures and torques to some extent. I often think of the shear one as being associated with torques, making sure that they'll respond safely and as you're expecting. Yeah?
What is the
So this was the pressure. Pressure is force over area. We haven't really defined that much yet. We're going to talk about it first thing in class on Thursday as we introduce fluids for the first time. So yeah, here this is the pressure. Let me just write that down to make it clear. All right, so let me ask, I'm not even sure I know the answer to this, but I once did. Those of you who are going to be worrying about building things, remind me why a lot of buildings are built with steel frames, but then have concrete. So the steel reinforced concrete, bridges, civil engineering. What are the special advantageous features of steel reinforced concrete?
So that concrete is good for compression.
Yes.
The steel is good for the tensile.
Yes, and I think it's also good for shear. So yes, that's why, if you look at how things are built, next time you go past a road being built or a bridge being built or parts of buildings being built, the reason they have steel reinforced concrete is it turns out to be a good combination under both tensile stresses, shear stresses, and tensile compression. So steel is very good when it's being stretched in some way, either longitudinally or kind of laterally. Concrete is extremely strong when it's compressed, okay? So the combination of the two is apparently what makes the good building materials. All right, any quick questions on this general stress-strain response? We are only going to worry about these types of relationships where we're in the linear response regime, it's still elastic, and we're simply going to work a few problems where the length changes or the volume changes. All right, I'm going to set up a problem because we have 5 minutes. I don't think we're going to finish it, but I want you guys to think about how you would solve it, just to make sure you're getting the sense of what we need to do with these types of problems. Okay, so here's an example. Again, it is and will be in my notes. Okay, so let me see if I can quickly describe this problem. This is a lead brick. It is resting on 2 cylindrical pillars. A and B. And let me tell you that the area of A twice the area of B. And let me tell you that the Young's moduli are also in a relation of 2 to 1. Write this with Y rather than E. Okay. And we are told that before this lead brick was placed on these things, the 2 cylinders have the same length, but they also have the same length after the lead block is placed on them. So A and B have the same length before and after the lead block is put in position. So bear with me, I know you're anxious to get going, but I want you to think about this before we close out. Okay, so the question is, what fraction of the block's mass is supported on each pillar? So just think about this for a moment. So, 2 equal length cylinders, different areas, different Young's modulus. Then I place this heavy brick on top. They both compress, but apparently they compress by the same amount. And we all we're told, and we're asked to find how much of the weight of this block is kind of effectively resting on each of the pillars. How would you do it? How would you solve it?
Start from the center of mass of the lead brick, and then, there's no net work, so you could use the different cross-sectional forces on each side being equal to each other. You don't have the distance from the center of mass of each facility, so. Okay.
Okay, good start. Yeah.
Well, I guess we can start off by identifying what type of stress it is. So we can go to the formula. So since there's the big load Young's modulus, we know that it's a tensile.
Right, so these 2 pillars, they're cylindrical cross sections, they're being compressed. That counts as a tensile stress. It's not uniform from all directions, which would make it hydraulic. So it's definitely a tensile one, yes. So this is going to apply. Okay. So now we know this is relevant for both of those cylindrical pillars. Now what?
In the problem, they gave us some initial values and locations to each other, so we can use that kind of information.
Okay, and the relation being what? What is it that is the same for both of these pillars? Yeah. Right, so delta L and L are the same for both of these 2 things. So when we're using this, these 2 are the same. So this is common for both pillars. then we're told something about these two in terms of relations between the two materials. This one of them has twice the Young's modulus of the other, and also has twice the cross-sectional area of the other. So in fact, simply by putting in those numbers, you should be able to get a relationship out of here of what is the ratio of forces acting in a compressive way on the ends of each pillar that makes that equation. So basically I'm taking everything over here. This is now F equals AY delta L over L. Delta L over L is the same for both pillars. And so by plugging in these numbers here, I should be able to figure out what the ratio of the forces exerted on each pillar is, and then we have to just do the comparison with the total overall force, which means the weight of this object. So, not difficult, but you'll occasionally have conceptual setups that are a little bit subtle and a little bit tricky. And in particular, you'll occasionally have problems involving volumes and bulk modulus that you just need to be careful about the relationship between change in volume and change in one or more linear dimensions, okay? Of course, volume is linear dimension to the power 3. Just be aware of that. Okay, we are done. A quick run through of performability. We're going to start on Thursday morning with fluids. See you then.
Thank you. No, when you're coming, you have 3 classes in a row? Do you need to call my guy?
Yeah.
Do you need to call? I mean, I already know.
At least we're not